let's look at two different ways that we can add vectors. Now, as with anything, we need as many tools in our toolkit that do the same thing as possible so that we can use them in different applications. So I've got two methods to show you. They're both important. Method one says just make the head of one vector be the tail of the other and draw a triangle to represent this information. So I've got an example here to do. If the vector A is equal to the directed interval PQ, now let's just draw that. So we've got A here, and it's going from P to Q, and the vector B equals the directed interval QR, in other words, going from Q to some other point R. Let's just draw R up here, and so it's going from there to there, and the arrow is going this way. Now, a word of caution here, just be careful that one arrow, when you put the next line in, doesn't completely obliterate that arrow and sort of make it confusing whether or not this is pointing this way or it's actually part of that one going that way. I like to have it finished just shy of the arrow there so that I can see what's happening. Now, if I've been somewhere, and remember that vectors are literally like an instruction to go from one place to another, then if I've gone along vector A and then along vector B, and I look at where I am now, compared with where I began, I've actually started here and I've finished here. So the overall displacement is that I've gone from P to R. So I've actually gone from there to there. And I can say that I could get from P to R two ways. I could just go here, or I could go there and then there. They're going to be the same total effect. So I can see that this way is going vector A plus vector B, and that helps me label this length here as vector A plus vector B. They're equal. So I can see here that vector A plus vector B is equal to the directed interval that goes from P to R. Now, this whole concept might be feeling really easy, or it might be confusing. The easy way to make it sit in your head nicely is just to say that when we're looking at the combinations of vectors, we're saying what is the net effect of our travel. And so here, if we want to get from this point to this point, from P to R, then we can clearly go there via vector, by following vector A and vector B, and adding those together gives me this net effect, and so that's why it gets that label. And now for method two, which says construct both vectors with the same tail and complete the parallelogram to show that there are two different paths to get to the same location. Now, this sort of example is one that you wouldn't use for an example like we just did. You'd use this one where they both need to actually have the same tail, and you wouldn't be able to use method one if you had a question like that. So let's redefine these vectors here and say that we have, let's say we're going from O to Q, and vector B is going O to R. Now, both of them are starting at O. So if you've got a question like this, method one won't work, and you'll need this method. So let's define vector A as going from O to Q with an arrow on the end. And vector B is also starting at O, but it's going to some other point R. Let's just make a random point R wherever we like and define that that is what vector B looks like. Now, once we've defined both of those vectors, remember a vector is a length and a direction. So if we want to do A plus B, then we'll travel along A, and when we get to our destination there, we'll say, right, now we need to do vector B, which means we need to go which direction? The exact same direction as this, so it needs to be parallel to that one. And how long do we need to go? Well, we need an interval that's the same length. So we can draw that exact same vector over here. That is also B. They are parallel and equal. Oh, mine don't look very equal. Sorry about that. Needs to be a little bit longer. And we're going to end up, oh, it still doesn't look very good. Dodgy as. How's that? That looks a little bit better. And we're going to end up here at another point, which we can say is the result of vector A plus vector B. But when we're adding two things, the order doesn't matter. So we can see that we could easily have done vector B first, and then vector A would come along here like this, and it's going to be parallel to the other vector A and the exact same length. Okay, my drawing's not perfect, but you're getting the idea. And we can see there that the order doesn't matter when we add vectors. And so this method is really important when we've got both vectors having the same tail. We really need to do it this way. And we've got two paths, so there's a little bit of variety on how to get there. So if we're adding these together, we would have some other point, let's call this S, and we would say that the result of vector A plus vector B, no matter which way we go, is that we get from O to S. So the directed interval would be something like that. Now, a couple of other points about adding vectors. When we add a zero vector, it doesn't cause any change at all. So if we had a directed interval like AB and then we add BB, well, we've just got to B, and when we get there, if we give the direction don't go anywhere at all, then clearly the overall movement is just from A to B. So it doesn't affect this. Adding vectors is commutative. Now, if you don't remember what that word means, that's okay. It just means that order doesn't matter. So we just saw that A plus B as vectors is equal to vector B plus vector A. That's quite straightforward. And adding vectors is also associative, which means that grouping them differently doesn't cause a change in the result. So an example here, if we're adding three vectors, vector A, B, and C, then whether we group A and B and then add C, or we do A plus the grouping of B and C, we get the same thing. Now, a little proof of that, I'll just leave the law up there and I'll rub this out and show you the proof of this with a picture. If we try and execute this little set of instructions, then we'd be saying, all right, let's make vector A look like that. And if we make up a vector B, let's say it goes, I don't know, here, it could be anything we like really. We're just making a set of instructions. Then we've already learned that this vector that goes straight from here to here would be called vector A plus vector B, because it's the net result of doing one and then the other. So if we have that net result, the part in brackets here, and then we add another vector C, let's say vector C goes to some other place, perhaps it goes up here, like that, then the net effect of all of this movement would be to do vector A plus B first to get to here, and then C. So overall, this is vector A plus B together plus C, this action here. But if we're to do it the other way and say, well, all right, let's just start by doing this part first that's in brackets. What is vector B plus vector C? Well, here's vector B, and if we then do vector C, we've gone there. So the net effect of that movement is to go here. We could call this line vector B plus vector C, couldn't we? And if we say, all right, the total movement we want to do A, that's going here, and then we want to do B plus C, which is going here, then effectively this set of instructions says go there and then go there. And the net effect of all of that is going all the way along, which means we could also use this set of labels for this directed interval here. And all it has that's different is the brackets in a different place. And we went a different path to follow out those instructions, but we ended up exactly in the same place no matter which set of instructions we followed. Subtracting vectors is relatively straightforward if we remember two things. Negative vectors have the reverse direction from their positive counterparts, and we need to construct the positive version of any vectors that we're working with the same tail. So this will make a lot of sense if we sort of show it with an example. If we have vector A minus vector B, now we can make these both have the same tail. Let's make vector A go here, and let's make vector B start from the same place, but go wherever it's going to go. Now, if we want a positive vector A, that means we want to travel along this path here. But if we want negative vector B, it means that we don't want to go from here to here. It means we want to go back that way. Now, we've also seen that when we are adding vectors, we can change the order. So can you see how this is exactly the same as negative B plus A? Now, it makes sense to do this one first, because you can see that if we're going to need this action going from here to here, and we need this action going from there to there, we sort of need to do this one first and say we need to go along that path and then along that path. Now, what will be the net outcome of that movement? We will have travelled from here to here. And what will we have done? We will have done negative B plus A. So now we can draw in this vector that goes this way, and it is negative B plus A. That's what we actually did, and that sort of, to me, makes sense. We started there, so we went minus B plus A, but we could also write that a lot more tidily if we write it A minus B. So I guess we often write it this way because it's tidy, but we think it through like this because it acts out the action a lot better. It acts out the movement, if you like. So to me, switching it to this makes a lot of sense. Now that made a lot of sense if we were just given the vectors and not the directed intervals. But you can see that this method only works if we've got vectors that have the same tail. So if we're given directed intervals instead of vector names, or perhaps we're given both, then we've got the same exact thing going on, but maybe you might construct your working a little bit differently. Now here, if vector A is the directed interval OA, then I could now name these points, which I didn't have before, and this would be B over here. So it makes sense to think, okay, I'm going to do the negative one first, and then the positive one, and then we could say, all right, what is negative B? As a directed interval, it's going from there to there, so it's actually BO, isn't it? And then we need to add OA, and the net movement that we've got there is that we've gone from B to A. So there we can get the exact same answer, but we're showing our working with directed intervals instead. Now that brings us to position vectors, because if we are subtracting vectors, then it's helpful if they have a common tail. And if they don't, we can make them have a common tail by creating these things. So position vectors relate points to some other reference point, and you can often choose that reference point so that it's convenient. You can name your reference point O for origin, and so then any point, say P, would have a position vector, OP, as a directed interval. So then subtracting position vectors is straightforward now because they're going to have a common tail. So let's have a look at how this works in an example. If we've got these points P, Q, and R, then obviously we could relate them with vectors that go between them, and those vectors could have names of their own and they could be described as directed intervals. But we could also relate them all to some reference point O, and a lot of the time we want to do that for a particular reason, and so now we have directed intervals that look like this. So we have OP, OQ, and OR, and these could now have names such as lowercase p, lowercase q, and lowercase r as vectors. So now if we're going, say, from point P to point Q, then sure, we can use a directed interval PQ to show that, but we can also label this distance in terms of the vectors P and Q, because to get from here to here, we need to go along here. Now that's not P, it's negative P, but then we also need to add Q. So we could write it as negative P plus Q, but it would be simpler, I think, to put the positive thing first and say that it's Q minus P. Similarly, if we're going from here to here, then we can label this as vector R minus vector Q. And we could have one from here to here, which would be vector R minus vector P. And one of the main purposes of doing this is that if you already have then some known vectors, then we can relate a lot of other vectors around the place to ones that were existing, even if we created those in the first place, rather than coming up with names for each individual vector, which doesn't really show the relationship between them quite the way that this does.